Everybody, it's such an incredible pleasure and honor to launch into March 2024. Can you believe it's been 4 years of Living Histories, March 2024 edition of Living Histories with Shelley, Copley's talk. Shelley, please tell us about Living Many, Many Histories.
A rather long history at this point. Well, so Sri, thank you for inviting me to do this. It's really an honor to be part of this series and to tell you about my path in science. Uh-oh.
You'll need to unlock your iPhone first.
Sri sounds like Siri, apparently. Okay.
Shelley, are you okay with that, or do you want to restart?
No, I'm fine. I buried the phone. Okay. So my path, my academic path started, oops, I can't advance slides. Okay. Back in high school. So I grew up in the poor side of Colorado Springs, Colorado, and in the poorest school district. And a couple days ago, I Googled my high school, and it is ranked 7,443rd in the nation. So it was a pretty poor high school then, apparently still is. There were no AP classes or IB classes, didn't even have a calculus class. Most of the teachers were uninspired and uninspiring. And I was really starved for intellectual stimulation. So I started setting up independent studies with some of the teachers. So I set up one with a chemistry teacher and one with a history teacher and one with an English teacher. And that one turned out to be a really important point in my life because I talked this English teacher into letting me do a study of the effects of alcohol and caffeine on learning and behavior in male white mice, which obviously has nothing to do with English. But he said if I would write a report at the end of it, he would sponsor this. So I went and I bought 9 white mice, 3 for alcohol, 3 for caffeine, and 3 for a control group. And I found a maze somewhere. And then I cobbled together 9 cages. And I really do mean cobbled together because I didn't have real cages. So I made sort of metal grates that for the top, and then I tied them to cookie sheets with yarn. And I put the mice in these cages. And so there were some problems with this experiment, not beyond just having 3 mice per group, of course, but so I would head home every day during my free period to run the mice through the maze. And sometimes I'd walk into the basement where I had this all set up, and the mice had gone to visit each other. And so there would be 2 mice in one cage. And that was problematic because I couldn't tell them apart. So I didn't know which cage they actually belonged in. And even worse were the days when I'd come in and the mouse was just totally missing. And I would typically find the stray mouse under the hot water heater, which was like this warm, dark place that they liked to huddle. So obviously I didn't get any decent data out of this study, but the reason that it was so important is that I wrote about this for my college application essays. And I got in everywhere I applied, and I'm sure it's because the admissions committees were rolling on the floor laughing about this kid out in Colorado Springs chasing mice around her basement because she wanted to do a scientific experiment. So I ended up going to Harvard because they gave me the best financial aid package. And it was evident within the first month that I was in way over my head. So most of the other students were from elite private schools or top public schools. And here I was coming from the worst school in Colorado Springs. And the problem was I didn't know how to learn. My approach to studying had always been read it really fast and cross it off the list. So I had a lot of catching up to do. And I had to learn how to learn while I was facing the hardest classes I'd ever seen in my life. But I did learn how to learn, and I ended up doing pretty well at Harvard, and I loved it. It was finally the intellectual stimulation that I had wanted. And it was in this beautiful historic setting, and the other students were smart and interesting. But it eventually had to come to an end. I had to graduate and move on to the next stage in my life. And all of my friends were either going to go to law school or medical school. And I certainly didn't want to go to law school. So I decided to apply to MD PhD programs because I liked the idea of combining medicine and research. But I actually ended up doing something a little different. I joined the Harvard MIT Health Sciences and Technology program, which was an alternative and more quantitative approach to the first 2 years of medical school. So it wasn't an MD PhD program, but there was the possibility of joining the MD PhD program after 2 years, which I did because I wasn't really that happy in medical school. We had to learn a little bit about a vast range of material. And that was just kind of counter to my intellectual proclivities because I really like to understand mechanisms deeper and deeper and deeper. So at the end of 2 years, I joined the MD PhD program, and thinking about what I might want to study for my graduate work, I realized that I'd always been incredibly fascinated by enzymes. And so I forgot to say this. We had a class of 25, there were 2 women. So I approached Jeremy Knowles, who at that time was one of the leading mechanistic enzymologists in the world. And I didn't actually appreciate that. I just knew that he studied enzymes and I wanted to study enzymes. So I joined his lab. This is a picture of most of the members of the lab a couple years after I joined. Jeremy was on sabbatical, so he's not in this picture. But one of the things that might pop out to you is that there are only 2 women in this picture. So this is me, and this is Carol, who was Jeremy's secretary. So of the 16 people in the lab, I was the only woman. But I had a great experience in Jeremy's lab. It was rigorous. It was, again, intellectually stimulating. I learned so much. I had a blast purifying enzymes and doing mechanistic studies. And then again, it had to come to an end. I had to graduate and move on to the next phase in my life. And so the logical thing for me to do would have been to go back and finish those last 2 years of medical school. But I was reluctant to do that for a couple of reasons. One was I had a 1-year-old baby. The other was that I hadn't really liked medical school that much anyway. And so I didn't want to go back and be on call every 3rd night for the next 2 years or however many years after that, when I was just happy as a clam in a research lab. So I decided to go straight on to a postdoc. And I joined a lab at MIT, which turned out to be a bad mistake because the PI of the lab that I joined was really out to prove that his favorite idea was correct. And that was really antithetical to how I'd been trained in Jeremy's lab. In Jeremy's lab, we were taught to evaluate hypotheses and to design elegant experiments that would differentiate between possibility A and possibility B, and maybe even something that you had never even thought of. So by the end of my first year at MIT, life was just not going very well. My baby daughter was calling her nanny mommy. I didn't like my science. My then husband didn't like his law firm. And so we packed up and moved to Colorado. And my thinking, honestly, was if I had 2 lifetimes, in one lifetime, I would pursue a career in academia in one of them. But since I only have 1 lifetime, maybe this is not the right career path. So I got a second postdoc in the lab of Tad Cook in the Department of Chemistry and Biochemistry at the University of Colorado in Boulder. And I immediately realized that that was a bad move, not because Tad Cook's lab was bad, but I realized that, wait, actually, I do want a career in academia. And I was worried that I had stepped off the fast track and that I had shot myself in the foot. But I got really lucky. 2 years later, the department was advertising for 3 assistant professors. So one was for an X-ray crystallographer, which I wasn't. One was for a synthetic organic chemist, which I wasn't. and one was for an environmental chemist, which I also wasn't, but I had a research program in my mind that had a strong environmental connection. And it had grown out of a day in the library at MIT where I happened to pick up an issue of Chemical and Engineering News, and the cover story was about white rot fungi that were able to degrade toxic anthropogenic chemicals. And I was really fascinated by the question of how microbes could evolve new enzymes to allow degradation of toxic chemicals that had been in the environment for only a few decades. So I had this program in my head, and I wrote it up as a research proposal and applied for the position. And to my shock, happy shock, I actually got it. So here's a picture of me in 1990 as a brand new assistant professor. If you look at this, I think that I actually look really terrified. So I got the job. I was delighted, and I launched, oh yeah, third woman hired in a department of 35. So I launched my research program looking at the evolutionary potential of promiscuous enzymes to be recruited to serve new functions in pathways for degradation of halogenated aromatic compounds that were new to the environment and toxic. So promiscuous enzymes are defined as sort of secondary activities of enzymes that normally serve other functions, but have sort of accidental side activities that can provide the starting point for evolution of new enzymes. So we worked on pathways for degradation of both of these molecules, but most of our work was directed at degradation of pentachlorophenol, which is a highly toxic compound that was used as a wood preservative and pesticide, and it was only introduced in the early part of the 20th century. So despite its recent introduction into the environment and its toxicity, there are bacteria that have been isolated from highly contaminated sites that can degrade this nasty stuff. So we worked on a pathway in a bacterium called Sphingobia chlorophenolica, which was able to convert pentachlorophenol into a sort of standard metabolite through a series of 8 steps. And we did a variety of things with this pathway. We identified the functions of 2 enzymes in the pathway. We did serious mechanistic enzymology on 3 of the enzymes in the pathway to understand how they were catalyzing these reactions and why they were really inefficient at catalyzing these new reactions. And we also looked at the origin of the genes that had been that encoded the enzymes that had been patched together in this pathway, and discovered that these 2 had been acquired by horizontal gene transfer. This one, which catalyzes 2 steps, had been acquired by a second horizontal gene transfer, and the ones in pink were pre-existing enzymes that had been repurposed for this evolving pathway. Okay, so that was good enough to get me tenure, but then I ran into a problem that couldn't be solved, and it had to do with my teaching load. So I was hired in a joint hire between an institute and the Department of Chemistry and Biochemistry, and they thought they were going to be hiring an analytical chemist, which I certainly wasn't. And so they put me in the organic division. And in this joint chemistry biochemistry department, the biochemist taught half as much as the organic chemist. And it didn't dawn on me for actually 10 years. I was a little slow. But I was a biochemist, but I was teaching twice as much as the other biochemists. So I asked the department to adjust my teaching load, and they wouldn't do it. It was, as you can imagine, a source of considerable friction in the department that there were differential teaching loads. So they wouldn't give me a biochemistry teaching load, so I decided that I was going to leave the university. And right about that time, I ran into the chair of the Department of Molecular, Cellular, and Developmental Biology in a stairwell, and we were chatting, and I told her that I was planning to start looking for jobs, and she said, well, why don't you come interview with us? So I went over to MCDB and I interviewed, and the faculty voted to take me in as a refugee. So I moved to the Department of Molecular, Cellular, and Developmental Biology in 2000, and it was actually the best move of my scientific career because it broadened my intellectual horizons massively. So I had been really focusing on the evolution of individual enzymes, and when I landed in a Department of Molecular, Cellular, Developmental Biology, it dawned on me that evolution takes place in the context of a cell or an organism with all of its complicated metabolic networks and regulatory networks. And that really changed the way that I looked at my science. So we started looking at the effects of mutations in genes encoding enzymes that were evolving, as well as mutations that occurred elsewhere in the genome, and investigating how those mutations had effects at the molecular level and all the way up to the cellular level. So, that really launched a new direction for me and, a lot of sort of intellectual growth in my lab over the next 20-some years. So one new direction was really prompted by frustration over studying this kind of pathway that had evolved in nature. So we could learn lots of interesting things, but what we could never do is go back and find the progenitor of the organism in which this pathway evolved. So we couldn't identify the mutations that had enabled this pathway to evolve, and how they had affected the new pathway and the physiology of the bacterium. So we turned to laboratory evolution, which is pretty simple. Basically, the idea is you put bacteria in a tube or a flask under some defined selection conditions, you grow them up, you dilute them and transfer them to new medium, and you do that for 100 or maybe up to 2,000 generations, and watch evolution actually happening in real time in the lab. And there,
Shelley,
yep.
this is your kind 15-minute reminder.
Okay, so the advantage of that is that we know the genome of the starting organism. We know what the selection conditions are. We can follow population dynamics, and we can identify mutations and actually analyze their effects at the molecular and cellular level. So a couple of other directions, we started turning our attention to not just evolution of new enzymes, but to evolution of whole metabolic pathways. And the idea there is that every proteome has thousands of promiscuous activities that can be patched together to generate new metabolic pathways. And we developed a model system to study that process. And then finally, the most recent thing is that we're moving beyond E. coli into several other microorganisms because different microbes have different toolkits for evolution of new metabolic pathways. And so we're finding that some organisms will evolve the same pathway by different mutations, and other organisms will evolve completely different pathways. Okay, and so the lessons that I have learned are to keep going when things are hard, to keep exploring and never stop learning, and don't be afraid to get out of your comfort zone and enjoy it, because this is a great opportunity to follow your curiosity. And finally, to nurture your trainees, because all of my career has been done in collaboration with dozens of great graduate students, postdocs, and undergrads, and it's been a privilege to train them and to send them on to the next stages in their career.
Thank you so much, Shelley. On behalf of the audience, I'm clapping. Audience, this is your reminder to please send your questions to me via chat. Shelley, I'll start by asking you about what you said early on in your talk about your having to learn when you went to this fancy place after where you grew up. With the benefit of hindsight, do you feel like the difference in how you learn things turned out to be a long-term advantage?
Well, I'd say I didn't know how to learn at all before I landed in college. And then when I when I landed in college, I realized that the point was to actually read and think and understand deeply and be able to use the information. And I guess that has, stuck with me forever. But it was I think knowing how to learn is not something you're born with, or at least I wasn't.
Um, Something that you mentioned near the end of your talk was how moving to this new environment and this new department was the best move of your career. So
Mhm.
would you please expand on what a happy move looks like? What about it was really awesome?
Well, actually, there are two things. I mean, one was just the different kinds of questions that people were asking in the MCDB department. They were asking questions that were really focused on organisms. And in the chemistry and biochemistry department, the questions are mostly focused on individual molecules. And so changing my focus from just thinking about the molecules to thinking about whole cells uh, opened up a whole new way of doing science for me. The other thing that was interesting about it was I mentioned I was the third woman out of 35 in the chemistry and biochemistry department. And I think I was always a subject of some suspicion because I had 3 children and I had to leave at 5:30 every day, and therefore I was not a serious scientist. When I got over to the biology department, it turned out that everybody had kids, and the men left at 5:30 to go get their kids, and so that was all fine. So that was kind of a shocking and wonderful transition to be in a place where it was actually okay to have a family.
Wow, on that very humanizing note, thank you so much again. I'm closing the recording.